All right, welcome everybody to the first of the fall colloquium series. This is the first one where we're transitioning from our summer schedule where the colloquiums were at 3 o'clock, now back to the 1:30 colloquia. And
the mic's not on.
The mic is actually apparently on, it's just not amplified, so I just have to stand here and you'll have to be quiet. We're taking over from Rebecca, and I say we because the colloquia were jointly organized by Nick Pitatella and myself this season. So for our first speaker today, we have BC Lowe. I think BC doesn't need very much introduction. He's well known to all of us here, I believe. But for completion, and because it's tradition, I shall introduce BC anyhow. So BC received his bachelor's in mathematics at King's College in London, New York, and then he decided that he wanted to be in physics instead. So he went and got a PhD at the University of Chicago, and he also was there a postdoc for 2 years. Afterwards, he was a postdoc here for a year, and then decided to take up shipbuilding for a few years. He did finally come back to the U.S. in 1980. He was a postdoc, an NRC postdoc for a year, and then became a scientist one in January of 1981 here at NCAR. Incidentally, BC has been at NCAR longer than I have been alive. So in 2014, BC retired after 33 years here at NCAR, and now, 2 years later, he's back to give the first colloquium of the season here. So, BC, please.
Thank you. Let me switch this on.
There we go. That should be good.
Okay, can you hear me? I'd like to begin by thanking Rebecca, Alfred, and Nick for inviting me. Hi, Natasha. For inviting me here to give this talk. And I should also say something about this unconventional affiliation that I have. It's not new to me. This is my family, the company that takes care of my family affair. I actually published 15 papers before I came to HAO using my father's shipyard as my affiliation. So anyway, let me start. Let me start by talking about, at least show a few pictures of what the solar corona really is about. So this set of movies from SDO is really very interesting to look at, in that you see white light sunspot group forming and the simultaneous measurement of the magnetic field, say positive and negative polarity. And we have this marvelous data nowadays to see how the active region actually forms. So these are all familiar to you, so I'm not going to run these things through. Let me get through all the images. Okay, so I always kept this set of images, the white light, the magnetogram for the line of sight magnetic field, the chromosphere above the surface, and the soft X-ray in the corona. And we see that the magnetic field that emerge into the corona, they don't just go away, they form, they reorganize themselves again and again with a lot of flaring and heating, flaring sometimes at such high temperatures, such as an event here seen in soft X-ray. And then they go on and on. Eventually, of course, the active region would decay. But what is remarkable even more is that when the active region is gone, the magnetic field don't just go away. The very thin filament you see in the active region, they erupt and they reform, and eventually what's left over will be a residual magnetic field, such as seen in this example, which is very impressive. It stretches for more than a solar radius, and it organizes themselves. So you don't see surface motion other than differential rotation of that scale. So this random magnetic field is very thought-provoking. How do they form? And eventually, as the sun rotates, you do see the effect of differential rotation. This structure gets sheared, and piece by piece, they leave the atmosphere through CMEs. So that is the physical system that I'm going to describe from a theorist's point of view, but I'm not so pure a theorist. I mean, these observations shall always be kept in mind. So let me begin with the MHD equation, one fluid for simplicity, and we have the momentum equation driven by the flow driven by a Lorentz force, pressure gradient, gravity, and of course you have your viscous forces. And you have mass conservation, and this is an induction equation, essentially your Faraday's induction, and there is a term for resistive diffusion, which I strike it out, and I'm going to justify that in a minute. And then finally, there is this awesome equation of the entropy changing due to sources in the atmosphere, heating, cooling, radiative transfer. So buried in here is a huge mass of a whole world of energy transport and atomic physics that I won't be going into. But this is a complete set of equations. And we say that the MHD equation as applied to the corona is near ideal in the sense that the resistivity is practically negligible. So to come to terms with that, let's look at what resistivity is in the corona. If you were to take Spitzer's resistivity, then the resistivity scales as the -3½ power of the temperature. You put in 1,000,000 degrees and about a kilometer length scale. So a kilometer is a good number because it's approximately the limit of your resolution when you look at the sun through your telescope on the ground. Then you find that anything involving resistivity is going to take longer than a year. So dynamically, it's not an interesting process at all. Now, observation says that the corona that we have seen over so many decades is clearly heated by the magnetic field as opposed to some other non-magnetic sources. If you accept that observational conclusion, then MHD, due largely to Jim Parker, has a very interesting thing to say. Now, high conductivity, meaning the resistivity is very small, actually leads to very efficient resistive dissipation. It does so by creating current sheets of very thin layers. And so this is not purely an induction effect, but it is a coupling between the force balances or force driving and the induction effect. And the sheets get so thin that however small your resistivity is, so long it's not zero, it will get to be so thin that resistivity at some point becomes important. So in that manner, a high conductivity plasma is also a very efficient resistive dissipative plasma. Now, the 1 kilometer length scale as a limit put up here has a terribly interesting significance. At the base of the corona, your mean free path is of the order of several 10 kilometers. And therefore, from here you can see that your corona overall length scale, as long as you want to describe it as a fluid, is practically ideal. There is no regime where this resistivity is ever going to kick in. So Parker's theory is very important because if no small scale ever arises, then the corona will be behaving as a genuine, perfect conductor, and there will be no heating. And it is because of this theory that you see scales forming, and they get smaller and smaller and smaller, and dissipation is not through classical resistivity, but through plasma kinetic effect, because your scale, as it goes smaller and smaller, it gets below the mean free path. So let's keep in mind that the corona is very much a perfect conductor, except if you could produce scales that are so small as to incur the plasma kinetic effects. And finally, there is a very important statement here. You see, the question to ask is this: if you get carried away with this theory, it's a very effective dissipative medium. Why wouldn't all the currents in the atmosphere shot away and all you've got is your potential field? And the reason is that when dissipation sets in your magnetic reconnection, and reconnection at high conductivity as opposed to a purely diffusive medium can only transfer magnetic flux and twist and not destroy them. And that is the conservation of helicity that was first enunciated by Taylor in 1974. These are very insightful ideas. Okay, so let me proceed and... Okay, so I'm going to provide you with some intuitive ideas. and then about what the conservation of helicity is about. And then for the rest of the talk, I want to talk about helicity as a theoretical idea. And I'm not going to go through a lot of mathematics, so do bear with me, ask me question. I think it's very exciting. Okay, by the time you get to the end of it, then you find that the pain was worth it. Okay. So the way this thing works is the following: you take say a uniform field, and you move the foot points around, and the fields get tangled up into some complex topology. And then if you were to take a slice right across this complicated field, you'll discover that very easily there are X-type neutral points that you can see on it. And it is across this X-type neutral points that current sheets will form in the manner Jim Parker was talking about. But what is so crucial to emphasize is in this picture, there's no null point. So how do you get an X-type neutral point without a null point? So here is a classical sketch of a Petchak reconnection where opposite fields across a null point come to meet each other and become so thin that the resistive effects allow them to reconnect, and the reconnected field with newfound tension force pull the reconnected field out of the way, and that's how the reconnection proceeds. But it should be borne in mind that BZ, the field out, the component out of the body, is not zero, such as you might expect to find, say, in the arbitrary slice across this tangled set of field lines. So there is this terribly long-standing fondness for null points. You don't really need a null point to have reconnection. And it was actually Sierowski who pointed that out. And Sierowski also predates Jim Parker in pointing out that current sheets should form very readily in a highly conducting plasma, and through their formation, because the sheet is so thin, that the resistive effect becomes important at some point during the collapse. But we mustn't live in a two-dimensional world. You see, in a complicated magnetic field, you might imagine there are three flux surfaces with few variations within each plane and across the planes. And they push into each other. And we're talking about very low viscosity, very low, very high conductivity. And we're also talking about astronomical scales, meaning the scales that make resistive time scale extremely long. So these are almost ideal plasma, and in three-dimensional space, when you push hard enough, two flux surfaces easily can come in, and everything gets scooted out of the way, and they come previously separated in space, come into actual contact. And that's the formation of a contact tangential discontinuity, and that's where the current sheets will occur. And this is really the basic reason for why current sheets would regularly occur, and yet they don't short everything to potential state. And that's because of the difficulty of getting rid of the twist and magnetic flux. So fields comes in, and fields that reconnect here get fluxes that are in these two lobes into the sides, and they take along with them the BZ component too. So there is a transfer of twist, and helicity in a very intuitive way could be described to be the relationship between different flux systems. And if you describe it in that sense, then you would say a reconnection reorganizes the field with some heating associated with the reconnection of resistive effect, and also a transfer of either flux from one system to another, or components of the field that changes the topology of one system when it gets transferred into another system. And that is a general thing that Taylor has. So the purpose of my talk is to describe to you how you might find a better basis, a theoretical basis to anchor these intuitive ideas. And it turns out there are lots of things we used to sweep under the carpet over the years, as you will see in a few minutes.
Could I ask a question?
Yes.
Yes, so in this context, do you think that the use of the term annihilation of magnetic field as opposed to reconnection is a bad?
I think it is. It was traditional in the old days,
Yeah.
because they felt that there's annihilation in the anti-parallel field were sort of mutually destroyed. And in fact, that's such a good point. You see, to annihilate a flux, you got to take two lines of opposite direction and lay them side by side along this entire length. That's how you annihilate. Otherwise, you only have reconnection. And reconnection, so at the end of it, I want to show you why it is so reasonable what Taylor said. You cannot get rid of flux. You cannot get rid of helicity or twist in the field on a very large scale. So this is what I aim to do, namely to provide for a theoretical basis so that we begin to feel more comfortable. We know what we're talking about. Okay, so let me go through the original classical ideas. I haven't done this for a long time, so if I try to be on time, okay, but bear with me. If I'm not on time, I want to get to the bottom line. So this is the well-known mass conservation equation. It is an Eulerian transport equation, meaning that it's so mathematically very convenient. If you tell me the density at each space point, and that's enough to describe the density distribution, where the mass is, but you don't track where each piece of material that you color pink, for example, has gone to. So that's your Eulerian description. But you could convert it into a Lagrangian description, meaning you're interested in knowing what happens to a piece of plasma, a particular piece, as you follow them. So you integrate for the total mass in this parcel of fluid that you're following, and you can show that the rate of change of the total mass is zero, as it should be. That's your mass conservation. And then, of course, for the overall domain, the total mass too is conserved. If you have an induction equation, you might say it's very inconvenient to deal with vectors. So, oh my goodness, my A here has come down. so you introduce a vector potential, and then you do A dot B, and then you can convert that into a scalar equation, more manageable. And this piece looks like your mass conservation equation on the left-hand side, but you have a source term on the right-hand side. And because it is a divergence of something, then this source term has a remarkable property. Life is very simple. If you happen to be dealing with a fluid at whose boundary the magnetic field is tangential, if that were the case, then the source term always cancels out. And then you can show that this piece, the so-called helicity, the classical helicity for a contained field, meaning the field is tangential along the boundary of the domain of interest, then that helicity is conserved. And that is origin of the statement that magnetic helicity is conserved. And if you were to apply this integral to two tubes of fluxes, and in this case, each one of them winds around the other 3 times, then that integral gives you a marvelous quantities, plus or minus, depending on whether the flux in these tubes are going in the same direction or opposite. And you have to multiply it by 2 because you're dealing with one twisting around the other and counting the twist, the mutual twist twice. And it's 3 times, so that's your linkage number, and then it's a product of 2 fluxes. But that assumes that these tubes don't have internal structures. If you do, then you've got to account for that. But this basically is your idea of a magnetic helicity. But it's very unsatisfactory because magnetic fields on the surface of the sun are anchored at the base of the atmosphere, such as given here a potential field due to magnetic sources on the surface of the sun, and the same magnetic sources with twists in it looks like so. And because it's not a contained field, the whole concept of helicity cannot be applied here. And yet, we know it has to come into the picture, say, through Taylor's theory. So to solve that problem, Michberger was the first to really successfully treat the problem. So the original contained field helicity is given this way, and I think one of the first to have dealt with this quantity was Elsasser in 1956. Michberger in 1985 published his PhD thesis, a real marvelous thesis with many citations if you go to look at. Nowadays, they are so crazy of a citation. Anyway, so Michberger did the following. if B normal is not zero at the boundary, it defines, I'm going to restrict myself to simply connected domains. And then it defines a unique potential field in the domain. If B normal is zero, the potential field in the simply connected domain is zero. So there's nothing to talk about there. So with the potential field, then you could think of the potential field possessing some kind of a helicity based on this formula, and the given field also have a similar helicity, and both of them are dependent on the gauge of the A that you use. But if you subtract them, and you come up with clear statement as to how you deal with the subtraction, then you can come up with a quantity called the relative helicity, which is gauge invariant, and then you recover whatever you've always been talking about using A dot B for the contained field. And this led us a very long way, allow us to look at magnetic field, magnetograms, and do all kinds of calculations. But it is really not the final solution to our headaches. Our headaches is more than just gauge independence. Our headache is to figure out what this quantity is, and similarly what that quantity is. The two loops that were linked 3 times that I showed you earlier on, they were so simple. Most magnetic fields don't look like that. Okay, and Mitch was my second postdoc at NCAR. He was an ESP fellow, and I used to, the two of us used to, look at this darn thing, and we didn't get anywhere. If we got ourselves, or he got himself, a gauge-independent quantity, I should be able to say something about a magnetic field without having to deal with the potential field, because you say this color pink, then I go look for a pink color. And that was what we kept thinking about, and we got nowhere. But finally, I got somewhere in 2011. So that's what I'm going to lead to, okay? So let me articulate what exactly is conceptually very bothersome. You see, there should not be any physics that is so different in terms of an anchored field versus a contained field. So I think this came from Jim Parker. You see, when the math gets too complicated, and then your concepts begin to get confused because of your mathematical techniques, so it's time to think physically. So one way to approach this problem is, I think the culprit is the vector potential. If I don't want to use the vector potential, can I get away with it? If I can get away with it, then I know that the gauge does have something to do with the problem. But if I can get away with it, then at least the difference between anchored field and contained field could be removed conceptually, in that fashion. And then the next point is something that bothered me only something like 10 years ago. You see, if you ask everybody what is the fundamental property of a eta equal to 0 induction equation, everybody will say it's flux conservation. So helicity has to be directly linked conceptually to flux conservation. If you don't, then you're forever going to trip over this idea, it seems to me. So maybe that's a place to start. And I should also talk about what do we mean by magnetic topology. We are so used to a lingo for so long. It was about 5 years ago that a referee wrote to me and said, rather unhappily, you never define magnetic topology. So I think that is where I should start. So what is magnetic topology? And then from there, we can make our way back to the more important questions. But this is important. So the induction equation without resistivity has a fundamental property, which is flux conservation. It says that if you give me any fluid surface sigma and calculate the total flux across it, then that is an invariant in this equation. And that is actually a Lagrangian property. In other words, you have to follow the flux surface, or not the fluid surface, as it moves through the fluid, and the total of flux across it is a constant. If the fluid surface, only fluids have motion, magnetic lines, magnetic surfaces have got no motion because there's nothing to identify it with. When we say this flux tube has an identity, we really mean that this flux tube contains the same fluid element at one point t equals to 0, at another point t equals to 1. So a fluid surface on which the flux is everywhere 0, that defines a magnetic flux surface, and it is permanently attached to the fluid that you're observing as it moves through the medium or through the fluid. So what is topology? If you go to the textbook, topology is about properties of some geometric object, and if you deform that object continuously, you don't tear and you don't glue, then all those properties that are still preserved in spite of your deformation, so metrics like length, angles are no longer valid, then those are your topological properties. So when we say that the magnetic field doesn't change topology, we are really saying that those fluid volumes containing the magnetic field, being real objects with a shape, the fluid preserves its topology, the shape of the fluid, and the field in it gains its property of a topologically unchanging magnetic field through its embedding in the fluid. And the idea is very simple here, but 3D fields are generally much more complex. So let me at least venture into that issue. I'm not going to go through the details, but I have to have some equations to be very specific about what I'm saying. When we are given a magnetic field distributed in space, we can calculate the lines of force by taking little pieces of a line element and subject it to being tangential to the local magnetic field, and we end up with 3 equations where S, the independent variable, is the parameter measuring the path length. And we'll get a solution up for each line of force, and there should be 3 constants of the ordinary differential equations. Since S is an ignorable quantity, so S sub 0, where you set S to be the starting point, is a free constant, and then there are 2 other constants of integration here. There will be psi 0 and zeta 0. Once you got a solution, you can take these 3 equations and invert and solve for S0, zeta 0, and psi 0. And then treating these constants of integrations as function of space, then every time you set this constant of integration, a particular value or particular values, then you map out 2 surfaces, psi equals to constant, zeta equals to constant, and 2 surfaces will intersect in the line, and that's how you actually geometrically define the line of force in terms of this so-called flux surfaces. So the first thing to discover the horror of mathematical forms of magnetic field is that this equation, which describes the lines of force as intersection of 2 surfaces, generally doesn't obtain for most magnetic field. They're only locally defined. So if we are given a magnetic field, it's always possible to locally define the flux surfaces, and where they intersect is the line of force. But generally, those flux surfaces that you define locally for a given magnetic field and the lines of force, if you extend it as far as you want to extend it, you find that they don't exist. And the reason they don't exist is that this set of equations typically will give rise to lines of force, point 1, that are infinitely long. And for the contained field, they are not only infinitely long, they can wind and wind and wind, unable to find the other end, and fill up either a volume or a flux surface. So if a line winds and fills up in the limit of its infinite length, a local volume, then so would the flux surface as a pair that defines it, fill up the whole volume, and all the usual idea of surfaces will break down. So this is a reality of most magnetic fields. And even if the field is not ergodic, there's a great tendency for field lines arbitrarily given to spread out with a Lyapunov number, one of these indices that says that it spreads out exponentially. I'm not going to need this, but I think we've got to keep in mind that real magnetic fields actually have this thing in there. And this thing makes any attempt to describe helicity in any form so full of problem, because you you run into problems applying to such commonly occurring fields. So let me see, where am I? Okay, just to give you a feeling for why there should be these ergodic lines. So imagine you have a very nice magnetic field tailored such that your lines of force are all closed. Okay, and then you give the magnetic field a small perturbation. In other words, you take Bx, By, Bz and give it a small little increment. Then, as you integrate for your original lines of force, these little pieces of thing start to change their direction, and unless you know how to control that change, it is very unlikely a closed field line is going to end up in a closed field line. So the way to look at it is that a line has got zero cross section. So you arbitrarily change the field in the volume, then it is very unlikely that you are going to hit your backside because you've got zero cross section. So a field filling up a whole volume is very common. And this is true of all differential equations, and this is exactly what your chaos dynamics is about. If you take a chaos dynamics, say in this case, a double pendulum swinging this way, any change in the initial condition by the slightest amount give rise to a very different path of evolution for the pendulum on the plane. It gives you, in other words, you could say the solution is not a continuous function of small displacement in the initial conditions. And it's for that reason that you end up with this mass. But this set of equations is very simple. It's on the plane. But for magnetic field on the plane, there's a solenoidal condition, so this phenomenon is not found in there. But once you get to the three-dimensional space, and there's only the next next dimension, there's no fourth dimension. So once you get into the next dimension, then the magnetic field will exhibit similar behavior. So somewhere in the picture, we also have to allow for whatever we call magnetic helicity, the possibility that the field you are dealing with is ergodic. As an aside, a flux tube is a tube of fluid centered along a few lines and of a certain finite cross-section, and there's a conserved total flux, magnetic flux along it. But ergodic field lines will imply that your flux tube is also a local property. You cannot expect to find the tubes that extends and remains whole. They split up for the reasons of egodicity. So with that in mind, let me go to the next step in what I'm trying to construct here. Which of these are the most direct and meaningful quantity? The magnetic field, the vector potential, or the magnetic flux? I think a physicist would say flux is the one that is really the quantity. For example, in the magnetogram, you measure flux rather than B. Hi, Natasha.
Yeah, I have a question.
Yes.
Just from a mathematical perspective, I mean, you can identify any two plane. If you give me one line in 3D space, there are an infinite number of planes upon which I can intersect to define that line.
Yes, that's right. Yes, and so the pairs of surfaces.
So the pairs of surfaces are infinite that you can define those lines on. So how are you going to pin that down?
No, we don't pin that down. So the pair of surfaces that define a line, is not unique, but the lines are unique. So then the surface, hang on, the pair.
The surface is the magnetic flux.
No, surfaces are not magnetic. The surfaces are the surfaces of zero flux. See, no flux passing through it.
Right, but there are an infinite number of surfaces.
Yes, there are. So the first thing to say is I have the lines that are unique because I solved those ordinary differential equations. Okay, allow me to say that first because that's where I anchor myself. Okay, then I got this two-dimensional array of lines, continuum of lines. Okay, then I can organize them into surfaces, and there are only two independent families of surfaces I can get out of them, and they are not unique. That's all. So I think that the thing that's discomforting comes from just that. Okay, so flux is really the physical quantity. In the magnetograph, as Bruce likes to tell me, what I measure is the flux, not B. Okay, so your flux is related to your B this way, and the direction of the little element across which you measure the flux is then the part that picks up the component of field in that direction. Of course, B is equals to curl of A, so you could have used Stokes' theorem and write it in terms of a closed path integral. Okay. This is what typically, even in the lab, you can only measure magnetic flux. So this is a physical quantity, and B and A are to be defined over a small and infinitesimal area across which you have that flux. And because A is related to the flux F by a path integral which is closed upon itself, that's why the gauge disappears. So here is the first clue why, Jesus, we got to do flux instead of A and B. So this is what I'm going to proceed, you see. And this has to do with the gauge invariance of classical helicity. I don't want to go into this. But the other thing I want to point out is that if you work it all out, each helicity is always a product of two fluxes, such as you saw in the case of two linked tubes. So now I go on to... So this part is more interesting. Can we not carry all our old baggages, go on and look for an explicit magnetic field, solve for it, and figure out what might be a conserved quantity that you could identify with helicity? So that's what I want to go through. I think I'm doing good with time. Okay. So let's take a extended magnetic field in the cylindrical domain of radius r sub 0 of length L. And in this domain, we want the field to be tangential at the cylindrical sides, and the flux comes through the bottom and out to the top, and we are given the normal flux distribution. So that defines a very specific magnetic field with its flux coming in a particular manner as distributed over one end and out the other end. Or maybe some of it comes back down, it doesn't matter. So now, very careful. I'm talking about a system that includes both contained as well as anchored magnetic field. And how do you want to solve this problem? You've got to find a representation of the magnetic field which is sufficiently general. And Chandrasekhar and Kendall in 1957, and this is very interesting, it was Kendall who published this, submitted this paper to the editor, Chandrasekhar at FJ. And Chandrasekhar discovered it independently, and between the person submitting and the editor, they decided to write this paper together. And this has been in the literature. Seldom people use it. I only know of one person, Natasha, who used something like that, okay? But this problem is not easy to do. But first, let me tell you what exactly this formulation does. It says that a magnetic field can be written in terms of linear superposition of two fields. One of them is this is psi, huh? Right, psi, okay. And never mind about what it is. Psi, you notice B sub psi carries a z component, and this other field doesn't carry a z component. So then B sub psi is taking care of all the magnetic vertical field component through each planes of constant z. Having done that, this field hasn't said anything about what lies in the horizontal direction. So that horizontal direction will contain a contribution from the residual part of the field, okay? And it's no use mixing the two together. So then we insist that this field, you notice the horizontal component is a gradient. And if it's just a gradient, the circulation on the plane anywhere is zero. So basically you're looking for a field that threads its way through as seen in the given field, but threading through its successive z-plane without its circulation, then all the circulation is then taken up by the second component, which is purely a field in the constant z-plane. Having done all that, okay, then this is how you're going to represent this field, and whether it is ergodic or not, the field lines is all included in there. So I've got a representation of a field which is completely general, and it will include all those awesome topologies and magnetic geometries. Then let's take the Chandrasekhar Kendall representation for the field and plug it into induction equation, and there you have it there. You see, the reason nobody uses beautiful formulation is because it's very hard to go from this to the boundary conditions for the psi and phi. And believe me, I tried so hard. And finally, I did it. So I got a boundary condition. Then I would say, look, this is your induction equation for two actually flux function, the flux going through vertically across the constant z planes, and the flux circulating around, they account for the twist, and the boundary conditions are given over here. Then never mind about helicities. Look at this set of equations and ask yourself, what can you construct out of it? A volume integral which is conserved for all time, and I got it down here. Okay, I mean, I did have a guide. I knew what, the classical helicity looks like. So I got this damn thing, and I got this boundary condition, and I work it out, and this is a conserved quantity. It applies to the field independent of whether the field is contained or anchored at the boundary. So the classical helicity is in there, but there's something else is also in there. When the field is anchored, there's no gauge problem because I'm dealing with flux, and therefore I call this the absolute helicity. And having obtained the absolute helicity, I can take Mitch Berger's relative helicity a step forward by defining the relative helicity to be the absolute helicity of a given field and the absolute helicity of a potential field. And incidentally, this quantity is not zero for a potential field, which is really new, okay? And I can do all kinds of things, but I know. So take, for example, if your field starts to evolve, your relative helicity may change or not change, but both quantities are changing, and there is an ambiguity in there. So all that can be settled. And they all have the same dimension of each helicity, whether it's absolute, relative, or classical, in the form of flux squared. And I'm not going to go through the properties of this because this other thing is more interesting. Now I come back to this fundamental question. It is flux conservation for across all fluid surfaces. That is a fundamental property. So I got to relate all helicity to that property, and to do so, I think I got 2 more slides, so I'm okay. Remember, helicity is a product of 2 fluxes. It's an integral, but it ends up to be a product of 2, if you like, average kind of fluxes. If you have flux conservation, any 2 fluid surface will each have a conserved flux. I multiply the 2 fluxes together, I got myself a helicity. It's a helicity in the sense of the same dimension, and each flux is conserved for all time, and therefore, I got a very elementary helicity, if you like. Therefore, the helicity that we talk about has to be somehow a way of summing. I mean, there's a 2-degree continuum of fluxes in all the fluid surfaces in a volume. So if you know how to sum these fluxes in some ways, and by summing it throughout the whole volume, then you would have a volume integral to express it, and that really is what helicity is about. Okay. So all I'm trying to say is, if I figure out I got a selection of fluid surfaces, they all conserve their fluxes, phi sub I, psi sub I, and if I multiply them together, I get myself a flux squared quantity, which I call the Lagrangian helicity. It is not like the old helicity. This thing only makes sense if you follow everybody where they went, because it's the Lagrangian property. Indeed, if I got this to be conserved, any function of these 2 guys to weight the product is also a conserved quantity. Then I would have a generalized Lagrangian helicity, and all hell breaks loose. But you expect that because there's so many fluxes you can define for all the conceivable fluid surfaces. Okay, I think this is my last. Oh, you're good. This is Okay, we go back there. Okay, that's the second field, B sub phi, lies on planes of constant z, and the closed curve, they account for the twist in the field. Therefore, every curve is going to be phi equal to some constant, z equals to some constant. So we've got all these curves, okay? And along each curve, you can define a tube of fluid of infinitesimal cross-section centered on each lines of force, and it will carry a certain amount of flux, little phi sub I. So this is the flux due to that magnetic field, and then the thickness in z direction of the cross section. So this is, I'm giving you a construction of the two fluxes on fluid surfaces. Okay, so this is one flux, and since this is a closed curve and there's a second field, then the tube of centered on the closed curve will have a hole through which this field will contribute a net magnetic flux across it, and that is also conserved. And therefore, the product of these two pieces will give you a Lagrangian helicity. Okay, and there are lots of ways of doing these things anyway, but this quantity is actually equal to this helicity for the absolute helicity that I got. So we are therefore almost there. We reconciled or brought together the idea of flux conservation across every fluid surface and the idea of helicity, and this helicity is a Eulerian quantity. Whereas these other guys, the Lagrangian quantity, to figure out what they are, you've got to follow the individual fluids. So let me then end with two very intriguing questions. Okay, one of them I have answered, So is it possible to take the Eulerian total helicity, whether it's classical, absolute, relative becomes secondary for our needs now, okay? So can we take that Eulerian total helicity and express it in terms of a Lagrangian helicity? And remember, Lagrangian helicity is based on which fluid are you following, okay? So there is always a particular fluid partition. Can you do that? The answer is yes, you can. Okay, it's it's non-trivial because if you go back, this is a conserved quantity. This is this piece. This thing is conserved as you follow the fluid, and this piece is changing as you follow in time. So this has something to do with the interaction between the right of a flux tube and the twist helicity. But anyway, yes, you can do it. And more than that, it turns out when you do it, remember there's a continuum of Lagrangian helicity which you can use to express your single Eulerian helicity. But the Eulerian helicity is conserved. Therefore, all those rich varieties of Lagrangian helicities with all the different fluid partitions used to define them, they all have the same value. So what do you get from there? You get from there this marvelous statement. In other words, if you do the Lagrangian construction, you discover there's a way of summing these conserved fluxes in such a way that is independent of which fluid partition you use. So this is what people call a rugged invariant. It is so rugged. It doesn't even give a damn which, so long as it stays within a set. And they are all conserved. And this is really what Taylor was postulating. There are certain helicities that are so rugged, even though you have reconnection, and remember, reconnection doesn't destroy flux nor helicity. And so these quantities as a volume integral remains approximately a good invariant. And I will tell you why I'm so excited. You see, I worked so hard to finish up here. And then by the time I quitted in 2014, I wrote a review article. I got everything except this Dunn theorem, you know. And then when I got my galley proofs, I saw it, you see. And right now I still haven't done it. But this is good because, you see, it gives you a physical feeling as to why there are rugged invariants. And in mathematical terms, you might say the Lagrangian helicity is a construct that is representation dependent, because you could tell me which fluid you want to pick out to select from the whole volume to define the conserved fluxes, okay? And then you end up with a true topological invariant, because this thing is independent representation. And if it's independent representation, then the Eulerian correspondence to it will have to be conserved, because it's equal to each one of these other things at different times in its evolution. So that question then leads to the second question, and I don't have an answer. You see, there is a two-dimensional continuum of Lagrangian helicities, because surfaces are two-dimensional, and therefore they are sort of two degrees of freedom to define two independent surfaces in a three-dimensional volume. Okay. So, in as much as these Lagrangian helicities defines a corresponding classically defined Eulerian helicity. But remember, I can take the conserved fluxes and multiply them. I don't have to limit myself to quadratic multiplication. And therefore, there is this generalized two-dimensional Lagrangian helicity, and therefore there should be a generalized Eulerian helicities. And are they conserved? I don't know. I think it's very compelling to think that they are conserved. And so this is a thought I want to leave behind with you. But in the remaining 5 minutes, let me bring you back to reality. Okay. This is a 1,000,000-degree corona, the big MHD picture. And it's very pleasing because there are two circular or cyclical chain of cause and effects. So observation says that it is magnetic heating and not something else. So the magnetic heating apparently can account for something like 1,000,000 degrees in temperature, and at that temperature and the stratification, you have the magnetic field dominate. So you have a field-dominated plasma. That high temperature gives rise to very high thermal conductivity, even if that thermal conduction is channeled around the field. And because then thermal conduction would take 1,000,000 degrees and extend it out way beyond the solar surface, then as you go further and further out, your thermal energy will exceed the local gravitational binding energy, and that's why you have a solar wind. The same temperature, 10 to the 6 degrees, give rise to an extremely high electrical conductivity. So if you take Spitzer's conductivity, and you can show that only for scale length larger than the mean free path, say put it down at something like 10 kilometers, 5 kilometers at the base of the corona, then you see very little having to do with the resistive effects in the magnetic field. But if the story ended there, then the corona should be cold as hell, but sitting at 6,000,000 degrees if you know how to heat it without the magnetic field. So the Parker theory shows that this magnetic field is constantly restless because it forms magnetic field ubiquitously, and that heating gives rise to the magnetic heating the observation demands for. You see, we can't observe these things at the scales that is happening. Now then, dynamo produces magnetic field, and they emerge into the atmosphere. And there's a preferred sign for the dynamo helicity on average, and it doesn't depend on the solar cycle. Each cycle is the same. In the northern hemisphere, it's negative helicity, bin dominant, and the opposite case in the southern hemisphere. And when the field enters into the atmosphere, it of course flares like crazy because the highly conducting plasma magnetic fluxes don't mix so well. So there's all this merging and self-organization of the twistor field. And the conservation of helicity ensures that whatever you have don't relax into a potential state. And therefore, we see at the end of each flare, as well as at the end of an active region's evolution, long-lived, hot macroscopic structures, and many of them are characterized by prominences sitting in magnetic flux robes. And these things don't sit there for too long because they eventually start to go out as CMEs. And when they go out as CMEs, the CME opens up a magnetic field. And mind you, the CME and flare phenomenon is so interesting in that much of the energy, the bulk of the energy in the CME is ordered motion. You see, which is, this thing says you can't get rid of the energy by flaring. So that you get rid of the energy by the CME leaving the atmosphere. And when the magnetic field opens up, the open field reconnects, and that is a class of flares quite distinct from this other one. This has got very little helicity left. This one will be helicity conserving. And the expulsion of magnetic flux and helicity into the wind is actually the principal role of the CMEs. And it actually gives rise to the reversal of the solar corona's large-scale magnetic field. Within 3 to 4 years of each solar cycle, the global magnetic field is reversed. And that is possibly having something to do as a boundary condition for the dynamo in the interior. So you've got all these things in here. So I would say we are in a very good part of the crossroad to do interesting questions because they can give rise to answers. So here we are. Thank you. I wasn't sure I had enough time, so I thought I should say this. That we are in very good shape. HAO has ushered in the era, Steve Tomczak and others, of coronal field observations, and there's ATST of NSO, and Macintosh has a remarkable set of observations that say you've got to think of mixing of fluxes from different adjacent solar cycle, then they're all this new work. And of course, I really want to thank all of you as representatives from generations of guys and women I worked with. Thank you. Sorry, I used up the whole hour. Hi, Mark.
Would you have that to slide 27, I think it was?
Which one is that?
Oh, you had your expression for the magnetic helicity in a cylinder.
Okay.
Yeah, at the bottom.
Yeah, at the bottom. Okay.
So if BZ is equal to 0, then the helicity should be 0.
No, BZ is not equal to 0.
No, I'm just saying in general. If it were,
yes,
then the helicity should be 0.
Yes.
But those two box terms you have there don't necessarily go to 0 if BZ equals 0, right?
Well,
it's essentially a toroidal field. Those are horizontal loops.
Yes.
And if you dot those into each other and integrate over the volume, doesn't that vanish?
I think it should vanish because if you see this piece of field is taking care of the B normal. So if B normal is 0, it can have a horizontal component, but that horizontal components economically are taken care of by that. So then psi is 0.
But I mean, it's just, so if you take each of those terms, the helicity comes from dotting one into the other, dotting sort of the A of one into the B of the other.
Yes. So
but
if this is 0,
individually, both of those is non-helical, right? Your B psi and B phi are both individually non-helical.
So if BZ is 0, psi is 0. And you can see why. You see, this is your BZ. And if the Laplacian of your psi squared, that's your BZ.
And then let me ask it a slightly different way. So that looks like a B phi squared type term. That looks like an A phi dotted into B phi.
Which one?
But that del cross,
right?
grad psi cross z dotted into 2 grad psi cross z.
Yeah.
The two orange boxes.
Yes.
That looks like a B phi dotted into A phi or something. I would expect that helicity to vanish.
Yes, it would vanish because psi would be 0 if there's no vertical component.
But I mean in general, even if there is a vertical field.
If there's a vertical field, then that dot would not be 0. You see what I mean? I can talk to you some more.
Yeah, maybe we should talk later.
Hi,
You said that for potential field, this guy might actually be finite still.
Yeah, because for a potential field, you got a BZ.
So this
Yeah.
psi, isn't psi really the superpotential for the toroidal field? Shouldn't psi actually be zero for a current-free field?
No, it does not.
So psi is not actually a
Yeah, it's
superpotential.
not. You see, if you look at this expression here, okay, for the potential field, this is 0, okay, and then you got this, okay, and this you can rewrite it in this fashion. Then this is your potential for your potential field, and being potential is Laplacian is 0. That's why the other piece doesn't come in. It was so astounding for me that for the potential field it's not 0.
And it agrees with the gauge invariant helicity of Berger field, you say?
Gauge? Come again?
With this absolute helicity, as we defined it, does that agree with the gauge invariant? It should, of course.
Oh, it should.
Yes.
But it does better than that. You see, for the relative helicity, okay, because it's measured relative to a potential field. So by definition, it's got 0 relative helicity. But it says nothing about what the absolute helicity would be.
So it's not the same then, actually.
Oh, it's not the same.
Yeah.
It's a difference between the absolute helicity of two fields that defines your relative helicity. And one of them is a reference field, which is a potential field.
Yeah.
And incidentally, conceptually, there's no reason why you should particularly care to use the potential field as a reference field. It really is just measuring the difference between two fields in helicity. And there's some very technical stuff in there too.
And can you also prove that this quantity is still a conserved quantity?
Oh, yes,
It
yes.
is, yeah.
Yeah, which was where I
Because
started.
it does look
So I
like-
started with the equations and boundary condition, and I discovered that this is a conserved quantity.
It has some elements of what suggests looks like a current helicity, right? Because
No, I don't think so. Current helicity is never conserved.
yeah, of course not, and therefore I was asking this question.
Yeah, it's not.
So it's and you can prove that. And which paper is that?
Go to Physics is Fluid 2011.
Oh, that's the one.
I noticed that nobody reads my paper, you know. No, somebody did. Jim Parker read my paper. And he said to me, this is really marvelous stuff. But nowadays, you know, the trouble with the whole community is that they don't read. But I was so busy, you know, I didn't go to meetings, you know. So this is, you see, imagine there is an absolute helicity. And that absolute helicity allows you to define the relative helicity. And because the absolute helicity of a potential field is not 0, that creates havoc. Because when you see a change in the relative helicity changing, you don't know whether it's a reference level that's changing or your field is changing.
Yeah, go ahead.
How do you calculate that your absolute helicity for a continuous field? Are you saying that you divide it up into flux tubes?
No, I don't. All those are continuous fields. Phi and psi are continuous.
Yeah, no, but this is one flux tube.
Oh no, it's not. It's a three-dimensional distribution of a given field.
But it's a field with a specific form, a limited form.
No, it's not. This is very general for any field in a cylinder.
The unit
Well,
vector of C
but
is
it's-
maybe special,
But
right?
it's cylindrically symmetric, right?
No, it's not. You see, there's this variation in R, phi, and Z. Take a look at that. This is a remarkable, and while you take a look at that, let me pose a very interesting question for everybody. This representation is only valid for cylindrical coordinates, spherical coordinates, or Cartesian coordinates, and no others.
Cartesian?
Cartesian, cylindrical, and spherical coordinates. And why is that? Now, I think I got some answer now, but this is so remarkable. Why is this beautiful formulation only valid for 3 particular geometries? Yeah, Yuhong?
When is the potential field's absolute helicity not 0?
Why is it not 0?
Yeah, why? I mean, what distinguishes those?
Oh,
different
so
potential
they are, yeah.
I mean, when you show that relation of your absolute helicity with the relative helicity, that view graph,
Mhm.
if you can bring it back,
Yep,
you have
sure.
it's the difference between the
Yeah.
absolute helicity of the real field versus
Yes.
over the
Yeah,
potential
here
field.
it is. Okay.
And you're saying that sometimes potential field
Yeah.
is not.
This
but
is
what
not.
is the why? What distinguish these different potential fields?
So
Is it
if
the side boundary condition?
no, it's not. If you give me a potential field, I can calculate the absolute helicity. Okay, I find that for some it's 0, others not. So what distinguishes between the two types of field? Axisymmetric potential fields for which this is 0. But a 3D field where B normal down below and B normal above are not the same, then that quantity is not 0. Okay. Now, what is so really interesting is this. Now, don't let me hold you back, okay? Because I can really go on like this. Now, so let me tell you something very interesting. This is where Oscar Merritt and I think some of you know Oscar. We had so much fun with this. If I were to take a potential field and anchor it at the two ends of a cylinder, then I hold the foot points rigid, and I contract that cylinder. Okay, I wouldn't have changed the topology of the field at all, right? Now, after you've contracted it, you're free to take the same B normal for the reduced domain and calculate the potential field. And you get another solution, potential field for the reduced domain. Okay. The helicity for both is the same. It should be. It is a true topological measure. But if you take the relative helicity in the two instances for any field, since the potential field has changed, right? And you discovered that your relative helicity actually changed, which is nonsensical because this displacement is topologically invariant. You didn't tear anything. And I think this quantity, which is well conserved and properly a topological property, is merely saying that there is a certain twist in your field because your B normal are not the same. And that cannot be ignored because it's accounting for the way the field is. Because you shot all the currents away, that doesn't mean you can destroy the asymmetry between the two fluxes. I don't have all the answers because I haven't had time to explore. But many of these things are very interesting because to begin with, it's difficult. But I think the key thing I want to say to everybody is that once you deal with fluxes, then you see the gauge problem completely evaporates away. It turns out to be possible. If that turns out not to be possible, then conceptually the gauge plays a role. In classical mechanics, the gauge is meaningless. In quantum mechanics, Aronoff, Bohm effect, the gauge of a vector, of a vector potential, plays a role in quantum mechanics, but not in classical physics. Okay.
I think I'm going to stop the discussion here because we're running a little bit over time.
Yeah.
Thank you, BC, very much for.
Thank you.
giving the
Thank you for coming.